I learned a lot this morning, and I hope I hope you can learn a little bit from my work as well. This is actually the work done by a lot of students, as you see the authors here. Yeah. So the first three authors are my undergraduate students. They're graduating next year, and to be honest, they did most of the work. Then we have two PhD students, and the last three are professors. And we learned a lot too from them. So this is a very applied work. It's related to cybersecurity, but related to the smart grid. So I'll tell you a little bit more about it. So our goal is to protect our electric grid. As we saw in California this past week, if we don't have electricity, it's a disaster. So we depend a lot on electricity, but the physical system, the electrical grid is very dependent on the communications technologies, the cyber component. And so this is where we come in. So I'm working with this power group from Texas A&M, doing the telecommunications part. And our goal is to learn how to detect those problems that may originate in the cyber, in the network, due to a cyber attack, or it could be even a physical problem, and then we can see, can we detect that from the network side? Could we have done something to improve? So there's also mitigation. But I think the main goal for now is modeling and detection that we're trying to do. So here's a picture from our proposal. We were very fortunate, so we can support and sponsor the work of all these students because we got a large grant from the Department of Energy. It's a 3-year grant. So we are completing our first year. And the name of the project is Cypress. So we found out a nice name. So Cypress is a next generation cyber physical energy management system. So as you see on the left side, the left side of the picture, on the top we have the power system, and on the bottom I would say the networking, how everything is connected. So this is the first step. We want to do the cyber physical model of this system. And then through simulations and also some experience, we're going to verify what happens, how dependent the physical side is from the cyber side, how problems in your network can cause problems in your power side. And the good thing is that we are working with industries as well. For instance, some industries are mentioned here. Vistra is a very large generation company in Texas, in Dallas. They purchased a lot of companies also. They have natural gas, wind. They gave us all their data. They're giving, not all the data, selected data, but they're giving us their data, the physical data. They have these historic databases, but then we're going to get those PCAP files as well. We're going to get real Wireshark files, and we're going to try to see how the problems they had were related in the network and the physical side. We also, so the second part is this, that we are doing some experiments with real data and verifying what happens, and hopefully we can do the detection. This is something the PhD students are doing. They're doing some machine learning, of course, to see if they can do some methods to improve the intrusion detection systems that we have in the networks, and finally some mitigation, but both on the physical and the power side. So this loop, so this is the main goal of our project. Hopefully we can do this in 3 years. It's a lot of work. I'll show you one thing that we decided to do, because for instance, to get data from industry, we have to sign a lot of NDAs, and for instance, the project started in October last year. We just got the data from the company this week, like last week. So it took a year to get the data. So we said we needed to find a model like a test bed. So we found out that we already have a model for the power grid. So we call this synthetic model for the power grid. It's done by one of the professors. He was a professor at University of Illinois, Urbana-Champaign, and he moved to Texas A&M. So I think we stole him. So he created this Texas 2000 bus model, has more than 2,000 substations. It's very interesting. He told us how he created the model. He had some knowledge of the power grid, but of course we cannot give this knowledge away. But he made up some locations using post office locations to create the substation. So he had zip codes. So it works well because the more urban areas have more, like the grid is more dense than other parts. So it's very interesting how he created the synthetic model. But when I went to his workshop, I asked, what about the communication side? Do you have any communication information for this model? I said, no, we don't. And that's where we came in. I said, okay, we can create a network for you. Based on this model, we are trying to create the, what are the, like the routers, the firewalls that goes in the substations. We have relays. The relays have IP addresses, so they control the circuit breakers. We are also emulating, one thing he doesn't have in his model is the control center. We created a utility control center. That's where the SCADA system or this energy management system is, sending commands and getting information from the substations. And also we had to create, I used to call a regulatory agency, but they corrected me. It's called balancing authority. So I think every state or region has, as I suppose, if you are generating too much power, or maybe during the summer, everybody's using their air conditioners, there's a balancing authority that tells the utilities you need to produce more power, or you need to make sure the grid is balanced and won't have any problems. So we modeled also the balancing authority. In Texas, it's called ERCOT. And this picture here is actually, we're fortunate. We have this lab at Texas A&M that emulates a utility control center. We have a software from General Electric that is really emulating a real control center. I'm sitting on the back there. These are all the students. So, but it's hard to make this work in real life, like we're emulating a real utility. So this is where we come in. So we have this model with several substations. So we have nodes and links. The links are transmission lines. So we converted this to a JSON file that has nodes and links as well. So this is initially our one topology of one part of Texas, the cyber model. And I found out this language, it's called Cyber Physical Topology Language. The original paper they did in XML, but actually the idea is very interesting. Like you model your network, but you add information about the power side. We add information about the substation. We add the application protocols that are being used, all those industrial protocols, such as DNP3, Modbus. So it's a hybrid. It has network information, most of it, nodes and links, but it has information about the power side as well, which bus it relates to. So you know if there's a problem in the network, we know which part of the substation is being attacked or which part will be at risk. Maybe we can isolate the physical part. So this is the main idea. So here's a picture of our model. It shows only one substation in the bottom. And I have the firewalls. I know a lot of people thought, oh, we have to put the firewalls, the routers first and the firewall. But actually, this is fine. The main thing we were worried about is one part we didn't know about the relays and relay controllers. So we got a lot of information from a company called Schweitzer and then how they model their local area networks. And of course, the substation needs to have a corporate network, like card readers, video cameras. these are not the OT network, the operations network. The OT network would be the one with the relays here. And then we have the operations center. There's always also a web server, a demilitarized zone that must be open to the public. And the protocol between the EMS, the energy management system, the substations that we are using, the layer 7 protocol is the NP3. But then I learned also about a new protocol between ERCOT, the regulatory agency, and the utility. We have this ICCP, is Inter-Center or Intercontrol Communications, or Intercontrol Center Communications. So it's an application layer protocol, and it's not protected. They don't run over TLS or anything like that. Of course, it's a very private network, very secure, like they have VPN. But I'm learning a lot about a lot of security that we use. For instance, we did SIP over TLS, HTTP, but these protocols, they are not using over TLS. So I see a lot of areas that there's a lot of opportunity if someone learns more about these opportunities for attacks. So overall, so there's a similar picture. One thing that I was going to tell you that, so this network that we created, so actually it needs to work with a power simulator. So the whole point of the synthetic model is that we are using the simulator called Power World. So we have to run real-time simulations. So we do the model, and we have to enter our model into the simulator, but it's not a discrete event simulation. It has to be real-time. So it goes back and affects your breakers. So things will happen. So we are trying to really create this cyber-physical simulation. Okay. So so this paper is mainly about the phase 1, creating the model. And we are still working on it, but we are already doing some simulation that I'm going to show you. But just to create the model, so we import data from Power World. So we have lots of tables about this Texas electric grid, the synthetic model. And then we have a Python script that reads those Excel files, and we create the JSON information. Similar to that CPTL language, the cyber-physical topology, nodes and links, and lots of attributes to those links. And one thing, so in our paper, we didn't show these. So we are using the simulation, and we tried a lot of simulators. We tried NS3, real-time simulation, but we ended up doing this core simulator. I don't know if you ever used it. I think it was developed by Boeing, and then it's a common open research. It's actually an emulator. Yeah, so we have virtual machines, and these talks with Power World, our power simulator. And we're working on a Python script that imports the JSON file into the simulator so it can build the topology automatically. So this is the current stage. But for the paper, we just had the cyber model, the JSON, and that's what we presented here. So this is the cyber model, the Python classes that we have. The main thing that we need to see is like we have nodes and links. Also, we have substation information, control center. And one thing I forgot to mention, one requirement that the industry asked us is to model different businesses. So we have multiple utilities. For example, in my city, I live in a small town called Station Bryan. We have 2 small utilities. So they wanted us to emulate also different utility control centers, different businesses as well. So we all put this in the JSON file. And one thing that we are working right now, we have to add the firewall rules. So we have an attributes part in our JSON. So we're adding all the rules, which protocols are allowed, like DNP3, ICCP, should we allow DNS? And then I was talking with someone. So we modeled this network initially to get some of the firewalls and to test. We use Cisco Packet Tracer. And when my student added all those rules, nothing worked in the network. I mean, she blocked everything, and then we have to see how a real utility. And we are having an industry workshop in a couple of weeks, and we're getting feedback on this topology that we are using as well. But the firewall rules, I think, is the most important that we are working to implement. So we can do assess the vulnerabilities of the network. So here's the use case. So Texas is very big, so we did the southern part of Texas, McAllen, so it's at the border with Mexico. So we had about 70 substations, and as you can see, we have the geographic location. We import from those tables, and then we created the network for that region. We created utility control centers, and we created substation with all those relays with IP addresses and routers as well. So it's a very practical work. And then, so the Texas model didn't have the utility, so we did some, we used that SciPy, and then we did some clustering, the workstations that more interconnected, and then we chose the central point to be the utility, and the regulatory agency, which would be ERCOT, we put in our campus. So our university would be the regulatory agency, but our goal is to do the whole Texas. But then we learned that our model is not very scalable. So that's all the scalability problem that we have in networks as well. But anyway, so as you see, just for that region, we generated like hundreds of nodes, routers, firewalls, all in this JSON format. The pictures that I show in the right, initially we were trying to use Splunk because it can, like because of JSON data, and it does the queries really well. We could do we tried to do the topology, but we found out that Splunk to do topology is not that good. It's not made for doing topology. We may use this for other things, but the pictures that you see here, for instance, importing from our JSON, we have a substation, we have the router firewall, and we have the OT network, the operations network with the relays, and we have the corporate network with the card readers, video cameras, some desktop for the operators. And at the bottom here would be a control center here, the EMS server, and several utilities connected to it, either through firewalls. But the way that we are learning how the utilities really have those, most of them is star topology. They have one firewall on each side. They don't advertise their routes. So it's a very closed network. So we are learning. So we are using this star topology to do. But now we are learning also that the substation, sometimes we may have inter-substation communication. This is something we don't have in our model. So all goes through the control center. But I think then it adds one more, maybe one more firewall or one more area to look after when you have inter-substation communication. Because you may have a small substation that uses a bigger substation to go to the control center as well. So a lot of new networking things that I'm learning from the power side. But anyway, so our work was mainly modeling, but now you know about our project. And then, yes, Carol? Oh, 3 minutes, yeah, so we're almost done. So I'm finishing. So one thing, we need to address is scalability because we have more than 2,000 substations. And our code, our JSON is huge. And we wanted to do something that we could do a zoom in and zoom out in our network. Because actually we wanted to emulate maybe even a blackout in a large region of Texas. So for this, I may not need so much detail about each component in the substation. So maybe just how they are connected. So we are trying to use this CPTL language, cyber physical topology language, to do the zoom in and zoom out as needed so we can address the scalability. Another thing, so we are working on the firewall rules, and we want to simulate several cyber attacks, and a lot of things that people follow. They want us to do something like, I don't know if you've heard of the Ukraine attack, that was several attacks combined. And that's one of the goals. And just on the last minutes, this is not in the paper, but I want to show you a little bit. We did a demo for the DOE last week, and we had the simulation in the middle. You can see the core emulator. So the red, so let's see if I have my mouse. The red is the cyber attack. So we had a man-in-the-middle attack, and we were doing a replay attack of some DNP3 packet. And it goes to the control center, but then we were able to show whatever that unreliable command was, it's an unreliable measurement, like a node measurement was sent to the control center, and then we put this in the power world, the power simulator, and made the grid unstable in some parts. So we demonstrated just one substation and one cyber attack. But now I think we can move on to do more substations, a larger scenario, and also address the scalability of the JSON model that we have. Yeah, but this is the latest, a couple of weeks ago we did. Yeah, but that finishes my talk. If you have any questions,